Okay, so first things first here. So we were talking about sketching polynomials yesterday, right? Yeah. So let's get all the phones and all that stuff away, please. Remember, a sketch is not a graph. Sketch is meant just to represent the important points on a graph. Like we want the x-intercepts. Later on, when we get to calculus, we'll add some other more important features to the sketch. Like we'll want to be able to locate all of the extreme points. So the extrema, the maxima, and the minima, and find the points of inflection and things like that too. Find slant asymptotes and find horizontal asymptotes and all kinds of other good stuff we'll add in calculus. But for now, we're really just worried about anchoring our sketch with the zeros of the function, the x-intercepts, and the end behavior. And that's about as much as we're going to do. And we want the sketch to look basically like the graph looks like, but just not exact. So how are we going to do that? So let's say we want to sketch this function right here, for example. What are some things we can do? Yes, sir.
Figure out the highest power.
Okay, well, yeah, what's the highest power going to be?
That's cubic.
Okay, so this is going to be cubic, all right? So you guys are, this is probably a little bit above and beyond what the textbook is saying, but the stuff we did yesterday, we did without the benefit of the trick I'm going to tell you today. And honestly, I think you probably could just, because you're so smart, you could do this just by thinking about this as a cubic with maybe some x-intercepts that we could look at and see by inspecting the function. The fact that it's cubic is going to help us how? What's that going to tell us? The end behavior. Good. That's going to tell us the end behavior, isn't it? So if we were to multiply this out, right, if we were going to expand this all out, which we don't have to do, all we'd need to know is that the leading term would be what? What would it be? Not x cubed. Negative x cubed. Right, I'd have a negative x squared times an x, which is going to give me a negative x cubed, plus some other junk which I don't care about, right? But the end behavior, remember when we looked at that function and zoomed out, the end behavior is determined by the leading term, right? So what kind of end behavior is that going to give us? What does this tell us about the limits of the function? So if we take, and let's go ahead and write this the calculus way. Instead of just writing it the way the book does. The limit of f of x as x approaches infinity equals what? Just got to play our sign game, right? What's that going to be? Gabe, if I plug in a positive number, what's the magnitude going to be? Is this thing, what size is it going to be? So it can be fixed or infinite? It's going to be infinite. Okay, so we know it's going to be infinite, but we just need to know what goes there. So if I plug a positive number, regardless of how big it is, if I plug a positive number in, what's the sign of the first term going to be?
Negative.
Negative. So negative infinity, right? What about the limit of f of x as x approaches negative infinity? What's that going to be? Maisie, what do you think? So we know it's going to be infinite, right? And we've got to know what goes there. So let's focus on just this first term. If I plug in a negative number, what am I going to get? I'm going to get a negative number cubed is what? Negative, right? Okay, so this part, so if we break this into two parts, if we break it into the negative 1 and the x cubed, when I plug in a negative number, this is going to be negative, and that's going to be negative. See what I'm saying? So what's the overall sign going to be of that first term then? Positive, right? And it's don't confuse the issue by thinking of it as being an infinity. It could be any number, right? All the infinity did was give us the fact that it's going to be infinite magnitude. It's going to blow up, right? But we just need to know the sign. We could plug in any negative number, and we're going to get the same sign back. You don't have to confuse yourself by making it something weird like an infinity. Just plug in a negative 1 if you want to. If I plug in any negative number, a negative number to an odd power is always negative, right? Whereas a negative number to an even power is positive. Okay? So we're going to get negative times negative is positive. And so that's going to be the left end behavior. Okay, makes sense? And keep in mind also, I'm writing this for you guys. I'm kind of getting you ready for the next step. But the way our textbook would write this statement right here would actually be written as, it'd say something like, as x approaches infinity, f of x approaches negative infinity, right? But this is just the proper way to do it, okay? So that gives us end behavior, doesn't it? Right? So now when we're doing our sketch, that helps us out. We know that the tails are going to be, for now, we'll just do this. The right tail is going to go down, and the left tail is going to go up, okay? What about in between, though? Let's talk about that. We'll get rid of this stuff. So that much we know. Okay, and we'll add some other stuff to this in a second. What else can we do? I'm going to get rid of this. I am taping this. I've been putting things up. Everything we do in class, I've been pretty good about putting them up that day. So if you want to look at this again later, you can. How could we figure out what's going on in here? Okay, so for one thing, we want to know where the x-intercepts are, right? We need to know where the zeros are. So what are the zeros of this function going to be? 4 and 0, right? And all we're really doing is we're just understand what this means. I mean, we've talked about this all in bits and pieces before, but what's really great about this section is it pulls it all together. So when we find the zeros, we're just setting y equal to 0 in solving, right? Everybody gets that? That's why we call them zeros. We're going to set the function equal to 0, aka y equal to 0, and find the x values where that happens. So we've just got this quadratic equation in standard form. What do you know, right? And by the zero product property, we're just going to ask the question, okay, when does that factor equal 0 and when does that factor equal 0? You see why it's so convenient to write out polynomials for these kinds of purposes. To write them in factored form is awesome. It reduces a lot of work. Now, later in the class, what do you think we're going to do? Well, I'm going to give you polynomials in unfactored form, and to do the same thing, what do you suppose you're going to have to do? Factor them. You're going to have to put them into this form, right? Okay, so the zeros are going to be x equals 0 and x equals 4, okay? So we know we're going to get zeros there and there, right? But we got to know what's going on in between, right? Here's where I'm going to show you another calculus thing. And this is so great because by the time we get to calculus, you will have already seen a lot of this stuff that students in the past hadn't really seen. So if we make it, now write this down. These tables they're worth their weight in gold. They're really good. So if you're going to start off at the top, that's going to be our x-axis, okay? This is how we can do a sketch. And actually, we're just going to maybe even get rid of this thing. And I'm going to. We don't even need this guy anymore because our sketch is going to come right from the table. Give yourself plenty of room. So that's the x-axis. We're going to make a row in the table for x and a row in the table for f of x, or we can even just call it y if we want to, right? Okay, so everything that we do that we've talked about can be summarized in this table. Let's start off with the domain and the end behavior. What's the domain of this function? Is there going to be any restriction on it? There's not, right? Graphically, when we graph it, we'll see that, but we talked a little bit about red flags yesterday, right? Was that yesterday or the day before? About places where you look. What are the two places for real numbers where we could have problems with the domain? What are the two things we can't do?
Divide by 0.
Can't divide by 0, right? And we can't take an even root of a negative number, right? Now, polynomials are what we call, and this is literally how we describe them in mathematical circles, we talk about them as being well-behaved because they don't have any issues. They're good kids. There's no chance of ever dividing by a 0 because there are no variables on the bottom and there are no even roots. So there are no red flags. So we know that the domain for every polynomial is going to be all real values. There's never going to be a restriction on what x values we can plug in, right? So in our table, here's how we show that. We go out to the left tail, and it's going to look just like interval notation. See that? So that's saying we're going to include the entire real line, or the entire x-axis is fair game for our sketch. Okay? You told me that the zeros were at the values x equals 0 and x equals 4, right? And we can include that information by putting a 0 in the y row. And so now do you see that these really are like ordered pairs turned sideways? If you like tilt your head like this, you can see them as ordered pairs. There's the x value and the y value, and just consider that to be the comma in the middle, right? What was our limit? I erased it, but you can tell me again, it was just negative x cubed. So the limit as x approaches negative infinity, what was our y value? Infinity. Positive infinity, and so we'll just write the word limit above that. So that's telling us what the end behavior is on the left. We'll write the word limit up there, and this was negative infinity. Okay. And then now we got to fill in the blanks. Okay, well here's where we can do some stuff. So let's graph a little sketch of our picture below here. So that's going to be the y-axis because it's at x equals 0. And here are x values 0 and 4, right? Those are x-intercepts. But we got to know what goes on in between. How can I test that? What could the function be doing? There's really only two things it could be doing between these x-intercepts. Okay, it could be tangent, okay, possibly, right? So it could be doing something like that, right? Or it could be, I guess there's a bunch, maybe there's more things than just two. What else could it do? So let's take a second and just graph all the possibilities. So one would be that it's going to do something like that, and then it's going to turn, and then it could do it again, or it could go through. So I guess there's some possibilities, right? There's a lot of different combinations of that. It could also go below, right? How could we test and see? What could we do? What do you think? And we know that's what our function is, right? Put that down here to help us out a little bit too, maybe. What do you think? How could we know? How could I test to see, really, I don't want to say anything, I want you to get it. I was starting to hear something. What were,
you can plug in, say, 1.
Okay. Okay, there we go. Let's try that. Let's plug in that's not what I want to do. There we go. Okay, yeah, back to business here. So, yeah, let's pick test points in between the x-intercepts, right? Does that make sense? So we really only got 2 x-intercepts this time. Let's pick a value in between, like, it doesn't matter what the value is. Could be, let's pick something easy. Let's go ahead and make it 1. That's fine. So 1 is a value in between 0 and 4. All I have to do is evaluate my function at 1. And I don't even need to know the value of the function. What do I need to know? Positive or negative? Sign. Is it above or below the x-axis? Right? So if we take f of our test point 1, what's the sign going to be? I'm going to get my negative times my x squared. Let's do that for a second. times x minus 4. That's f of x, right? If I break it up into all the factors, I've got a constant factor times my x squared times my x minus 4, right? Three things being multiplied together. So f of positive 1, what are the signs going to be? What's that sign? It's negative, it's never going to change. What's that sign? Positive. And it's, it's always going to be positive because it's squared, right? And then what about this one? Negative. So what's the overall sign? Positive. Negative times negative is positive times positive. How could I do, but what if I had a really complicated one? How could I look up there and just tell right away whether it's positive or negative?
There's an even amount of negatives.
Say it again. What's that mean? If there's an even, keep going.
There's an even amount of negatives, it's positive.
Okay. And if there's an odd number of negatives being multiplied together, it's negative, right? So the answer is, all we need is the sign, positive, right? And we know the end behavior, and so really that's it. Although technically, we could have even maybe gotten the end behavior here by just checking a point out here, couldn't we? Right? You see that? Because the only place that it crosses the x-axis is there and there. So I know, we'll fill in that blank in a second. Let's just take this information and make our sketch then, right? What's this thing? Well, okay. Yeah, let's make our sketch and then we'll fill in a few more things just to clarify some points. So what's this tell us? Well, we've already got the x-intercepts. This is telling us that in between, it's going to be up here somewhere. It's going to be positive. And the end behavior is down.
No.
Oh, well, that's supposed to be up, isn't it? Yep. Oh, it is up. Yep. So it's up and down. What's the only way I could graph my function and have that happen? Yeah, it's got to be tangent there, doesn't it? Right? See what I'm saying? Has to be. So it's going to do something like this. It's going to go like, right? And on this side, it's just going to go down. See what I'm saying? Has to be that way, doesn't it? You see that? Well, were you thinking, well, maybe, why does it have to go? Maybe it went down and went back up again. It can't do that. How come? Say it again. Say it louder. Yeah, we would have had to have had another x-intercept then, right? But this is a comprehensive list of the x-intercepts. There can't be any other ones, or there would have needed to have been another factor, right? You see what I'm saying? Isn't that cool? So from that little bit of information, you can fill in all the blanks. And if you just want to clarify this a little more, if you're just not sure, well then try -1. Put another test point in. If I put -1 in, what am I going to get? Negative times positive times negative, right? Which makes the overall sign positive. So sure enough, we have to have a test point out there that's above, right? Same thing over here. If I want to pick 10. If I pick obvious ones, if I pick 10, I'm going to get negative times positive times positive, negative. Well, sure enough, there it is. Right? Get the idea? Okay, try one. Try one of those. In my mind, this is maybe the most important thing we've learned. Okay, try that. Let's see a sketch of that. And I want to see the table. So when we do the test over this stuff, this is going to be, at least part of this is going to be a paper and pencil test because I want to see the tables. And I'll tell you that I've taught calculus for, I don't know, 20 some years at different levels, you know, at high school level, college level. And this is the thing I get the most feedback from students when they go on to the next level is the tables. That's the thing that they find the most useful. And honestly, that's kind of my own little thing. That's something that I did as a college student, and I've just brought it on, just kind of worked for me, and I've just brought that on into, I teach other people the same thing. So it's not something you're probably going to see, and you see different variations on it, but I really think this is the best way to do it. I think it's the most efficient way to do it. And so, you know, this is the one thing, really, just put this in your notes, and, you know, when you go on, you know, past calculus, this will be the thing that you'll come back to in differential equations and higher level math classes. That tabular form of organizing a function is unbelievably helpful.
So when's that test you're talking about?
Oh, soon. I mean, we're probably a week away at least. It'll just be, we're not going to cover a ton of sections. So what'll happen on the test is there'll be, I'm working on trying to build some Moodle problems for this stuff, but they're so hard to build. So I'm a little behind on that. I'm trying. Worst case scenario, we'll just do this whole thing on paper and pencil. But even if I am able to get all these Moodle problems built that work for this stuff successfully, probably the best case scenario in terms of what we'll do on a computer is there'll be a part of the test on the computer, but I am going to have you do some problems on paper and pencil because I want to see the tables. I want to see them. I mean, I'm going to grade your work on that. I just want to see the tables written out and filled in, populated, showing me the end behavior, showing me the domain. All that stuff we did, I want you to try to be able to get, you know, show that on the table and turn it into a sketch.